How was your?
It was okay. How was yours?
No, I didn't. I wasn't. I don't want to do math. Shut up. So, I just want to try.
I'm okay figured out it wasn't invitational for track, but we weren't supposed to host it. It was supposed to be Carrollton that was hosting it, but their stadium was under construction, so they borrowed ours to host it.
So they were like, mine.
I don't care about my past week.
All right. This week, each day, we are going to review one of the major topics of calc. Okay? And then we'll mostly look at multiple choice questions that go along with that topic. Next week, then, we're going to look at the different types of free response questions. So today, we're going to do limits and continuity, tomorrow derivatives, Wednesday application of derivatives, Thursday integrals, Friday application of integrals. So this week will be kind of our big review of calc with multiple choice questions, and then next week we'll look at how all that applies to free response questions.
So their only homework going to be this next?
No. So in the papers that you have, okay, I went through and pulled a bunch of limits and continuity multiple choice questions from past tests. So after we go through this quick review, I think there are like 15 multiple choice questions that are just limits and continuity. So that's what we're going to do every day this week, right? We'll go through a quick review over that day's stuff, and then there'll just be multiple choice questions that deal with that topic. Then next week we'll look at free response questions.
And this is due next Friday.
Next Friday, May 10th. I'll try to get it all ready. I know. I'll try to have it ready by tomorrow. I don't know if I'll have it all ready, but I'll try. All right. Limits and continuity. The basic idea of a limit, okay, is just that a limit is the y value that we are approaching as we get closer and closer to a certain x value from both sides, which is a two-sided limit, or just from one side, which we talked about as a one-sided limit. The actual y value doesn't matter. All that matters is the y value that we are approaching. So, for example, in this picture here, this limit, as we get closer and closer to an x value of 2, does exist. Even though there's a hole there, we are approaching the same value from both sides. So here, what we would say is the limit as x approaches 2 of this function is equal to whatever y value is getting closer and closer to. In this picture, we're getting closer and closer to 4. And so the two-sided limit in this example exists. So we looked at graphical limits. Okay, that's kind of what we focused on more at the beginning of the year. And then once we learned L'Hopital's rule, we spent a little more time doing the algebraic stuff. So let's start by trying to refresh our memories on some graphical ideas here. So we just have two graphs. The one on the left is f of x. The one on the right is g of x. So the first couple of questions are about f of x. So the first one says the limit as x approaches 0 of f of x. So that's saying, well, if I look at the graph, am I approaching the same value from both sides as I get closer and closer to an x value of 0? Well, yes, I am. And I'm getting closer and closer to a y value of 0. How about b? As x approaches 1 for f of x. Doesn't exist, right? I'm approaching different values from both sides as I get closer and closer to 1. So here we would say this one doesn't exist. How about as x approaches 2 for f of x? Also doesn't exist, right? I'm approaching different y values from either side for this one. How about for g of x as x approaches 0? 2. As x approaches 1?
No, wait. 3.5.
It exists because we are approaching the same number. Right? So I would say that's about 3. Right? Even though the function is defined here, all that matters is that we are approaching the same value from both sides. So the limit does exist for this one. How about as we approach -4? Doesn't exist. All right, so now the next few talk about one-sided limits. So remember, if we have a negative sign up here that kind of looks like an exponent, that notation just means as we are approaching 1 from the left. So for f of x, as I'm approaching 1 from the left, we are getting closer and closer to a y value of 1. So even though we said the two-sided limit at 1 doesn't exist, we can still talk about the one-sided limit. We can still talk about the value we're approaching from either side. So as we approach 1 from the right, we are getting closer and closer to
Oh, 3.
3, right? So x equals 1 from the right, we'd be looking at this piece up here. So we'd be getting closer and closer to 3. So, are you like if this were a closed dot? Is that what you're saying? So if this were a closed dot and this is a closed dot, this wouldn't be a function because it wouldn't pass the vertical line test, right? We would have two places where the function is defined at the same x value. So you're probably not really going to see anything like that. I mean, they're pretty much just going to give you functions. They're not going to try to, because that's more of a pre-calc idea. That's not, we don't really do anything, vertical line test and that kind of stuff in calc. So you're probably not going to see anything like that. How about I, as x approaches -4 from the left for g?
-1.
From the left, I think it would be 1. Right. So zoom out a little bit here to get the rest of them. All right, so now let's look at combining some of these. So when we talked about limits, okay, we talked about some limit rules that basically said, well, if I'm dividing or multiplying or adding, I can just split those up into separate limits. So here, I could say this is just the same as the limit as x approaches -infinity of g of x over the limit as x approaches -infinity of f of x. Right? We're just thinking about those as separate things, and then we're going to divide whatever answers we get. So for g, what's the limit as x approaches -infinity? 1, right? And what about for f? Infinity, right? We're going to infinity. So what is 1 over infinity? 0, right? So we would say that this limit is just 0. Remember, any number over infinity, we say is just 0. So for k, we want to multiply two limits together. So as x approaches 1, what's my limit for f of x? Doesn't exist. What about the limit as x approaches 1 for g of x? 3. Right. If we're trying to multiply, does not exist times something, that's just going to be does not exist. L, limit as x approaches 0 of f of x over g of x. So just like j, I can find these two limits separately and then divide. So the limit as x approaches 0 for f of x was 0. And for g of x, it's 2. So 0 over 2 is just 0. last 3. So m, I'm just flipping that. So instead of 0 over 2, we'll have 2 over 0. 2 over 0 wouldn't exist. Right? We can't divide by 0. So this we would just say does not exist. Then n, the limit as x approaches negative infinity for g of x. So, yeah, as we go to negative infinity, this function is just staying on y equals 1. And the last one, as x approaches negative infinity of f of x over g of x. Well, we already did g of x over f of x, so we're just flipping j here. So this would be infinity over 1, which would just be infinity. Right? Feel okay with those? All right, so on the next page then, talk about algebraic limits. So algebraic limits, we did a little bit in the beginning of the year trying to do some algebraic manipulation before we learned L'Hopital's rule. Okay? But now, most of the time, whenever we need to evaluate a limit algebraically, we are going to use L'Hopital's rule. So, the first thing that we should always do is plug in the x value in question, even if that's infinity. Right? Plug it in and see what we get. If we get an actual number, that's it, we're done. That's the answer. Okay? If we get something over 0, the limit doesn't exist, and we're done. The third option, which is going to be the more common one, is if we get an indeterminate form when we plug in our value, which means, for our purposes, 0 over 0 or infinity over infinity. I mentioned before there are other indeterminate forms, but those are the ones that we'll see, 0 over 0 or infinity over infinity. Then we use L'Hopital's rule. L'Hopital's rule just says, if we get an indeterminate form, then just take the derivative of the top and derivative of the bottom. Make sure that we don't confuse this with quotient rule. This is different than quotient rule. So let's take a look at a few of these real quick. And we're not going to have time to go through all of these, but go through a couple of them. So on number 12, the limit as x approaches 0 of sine of 3x over x. So first thing I need to do is plug in the x value. It's always what I should do first. So if I plug in 0, it's sine of 3 times 0, which would just be sine of 0. What's sine of 0? Sine of 0 is 0. So I would get 0 over 0. L'Hopital's. Okay. So we need the derivative of the top. So what's the derivative of sine of 3x? 3 cosine of 3x over the derivative of x is just 1. So now we want to try to plug in our value again. So now if I plug in 0, I'll have 3 times the cosine of 0 is 1. So I'll just have 3 times 1 is 3. Alright, how about the next one? The limit as x approaches 2 of the secant of pi x over 3. Plug in 2, right? Always plug in this value first. So if I plug in 2, I would get secant of 2 pi over 3.
Would that be considered?
Yeah, secant is one of our cosines. So if this were a free response, yeah, you could just leave it like that. But more than likely, something like this would show up on the multiple choice. So we could say this would be the same as 1 over cosine of 2 pi over 3. equals cosine of 2 pi over 3.
It's one of the weird ones.
I'm just saying that's what it is. I don't know if that's what
Wait, what?
like she's not saying. Yeah, I'm not saying that's her answer. I'm just saying that she's very.
It goes 1.
So where is 2 pi over 3 on the unit circle?
It's
Approximately.
over here-ish.
Up here somewhere, right?
So it's negative 1? No. No, it's not. It goes so it's
Well, it will be negative, right? Because we're talking about the x value, and we're to the left. So if we're thinking about the x value would be greater, well, technically less, right? So a larger negative number here than it is here. So this one would be negative square root of 3 over 2.
so that's
So you had, your thought process was right, just backwards. Yeah.
so it does that one.
So negative 1/2. So we would get 1 over negative 1/2. So negative 2.
You did not give them space.
No, not for these questions. All right, let's do 14. So on this one, we can look at 0.
It's going to be 0 over here.
We get 0 over 0.
So if the derivative is going to be 1 plus cosine of x over 1. Is equal to.
One small notation idea. When we are using L'Hopital's rule and we rewrite it with the derivative over the derivative, we do need to include the limit notation when we rewrite it the first time. And it's only when we plug in the value then that we don't have to include the limit notation. All right. We okay on those? Let's see. Let's do one more. How about 17?
You're going to have 0 over.
You're gonna have 8.
It's 8 minus, so that would be 7 over 0. That's not equal.
Right. Okay, here, if we plug in our value, we get 7 over 0. So, in this case, 7 over 0 does not exist.
So it.
So we would be done. Right? You feel okay with those?
Yes.
Alright. Actually, let's do 19 as well. So on this one, if we plug in 0,
You get.
yeah, so we would get 3 squared is 9, so 9 minus 9 is 0 over 0. So we could use L'Hopital's rule. Yeah, so this would become the limit as h approaches 0 of, so this derivative would just be 2 times 3 plus h to the first power times the derivative of the inside, which would just be 1, okay, minus 0. Derivative of 9 is 0 over 1. So now we can plug our value back in. So, right, we would just get 2 times 3, which is 6. Right. Good on those? All right, so really the last idea here was continuity. So,
The one I always have problems with.
let's take a look at continuity. Our calculus definition of continuity is that the left-hand limit equals the right-hand limit equals the function value. All three of those things equal the same value. Then the function is continuous at that specific value. The most popular way for this to show up on the AP test is a piecewise function. And like this example right here. So we're defining f of x to be this piecewise function. And this was actually part of a free response question on the AP test. It says show that f is continuous at x equals 0. To do that, I need to check all three of these things. Whenever I see continuous, okay, I should be thinking I need to check the left-hand limit, the right-hand limit, and the function value. So to do that, right, let's say the limit as x approaches, so we're checking for 0, so I want to say the limit as x approaches 0 from the left. Well, if I'm looking at my function here, which piece is approaching 0 from the left? The top piece, right? Because this is the one that's defined for x less than or equal to 0. So I'm approaching from the left here. So I'm going to plug 0 into this piece. So I'll say 1 minus 2 times the sine of 0. What's the sine of 0? 0. So this would be 1 minus 0, which is 1. So the limit as x approaches 0 from the left is 1. So let's check the right-hand limit. So the limit as x approaches 0 from the right. So that would be my other piece of this piecewise function. Right? If this is defined for x greater than 0, this is the piece that I will be using to approach from the right. So this will be e to the negative 4 times 0 power, which would just be e to the 0, which would be 1. We also have to check a third thing. We have to check f of 0. So f of 0, so which of these pieces is actually defined at 0? Top, right? Because it says x is less than or equal to 0. So we already evaluated that. Right? 1 minus 2 times sine of 0 equals 1. So we got that all three of those pieces are equal, right? They're all equal to 1. So let's write out a little sentence here. We can say since the limit as x approaches 0 from the left of f of x equals the limit as x approaches 0 from the right equals f of 0. Okay, it's saying they're all equal to 1. Then we can say f of x is continuous at x equals 0. So these three things, left-hand limit, right-hand limit, and the function value. Check all three of those to show that a function is continuous. Great, or we could use that the other way as well to prove that a function is not continuous at a certain value. We would still check those three things and say, well, these two things aren't equal, therefore the function is not continuous at this value. So this type of question then, determine the value of c such that these functions are continuous. Okay, well, if I'm looking at this first one, the only places where this function might not be continuous is at the break, right, at x equals 5. So what I would want to do to find a value of c that does make them continuous is set each piece equal and plug in x equals 5. So I'm just saying 3 times 5 minus 2 equals 5 squared plus c. Solving for c. So we get 15 minus 2 equals 25 plus c. So negative 12 is equal to c. Okay with that type of question? The AP test loves piecewise functions. They also like tables. So real quick, intermediate value theorem. So the intermediate value theorem basically just says, if we have a continuous function, then the function is guaranteed to take on every y value in between two endpoints. So we're saying, if I've got these two endpoints, right, A and B, then this is my y value associated with each point. If this is continuous, no matter what the function does, right, I'm guaranteed to hit every y value in between. That's all the intermediate value theorem says. So we can use the intermediate value theorem then to guarantee things like what part A is asking here. So we're defining h to be this function, f of g of x minus 6. And then we're saying, well, explain why there must be a value in between r equals 1 and 3 such that h of r is negative 5. Okay, well, here I would just want to evaluate each of these endpoints. So h of 1 and h of 3. I think we're going to run out of time. Right? But what's going to happen is that we'll get a value less than negative 5 and a value greater than negative 5. So we would just say, well, by the intermediate value theorem, we're guaranteed that since this is continuous, every y value between, I think one of them is negative 7, the other one's 3, every y value between negative 7 and 3 will be hit by this function. All right? So the rest of these papers are just multiple choice questions, okay, pulled from these previous AP tests. So your homework tonight is to finish these questions.